The last major topic in the course is that of Fourier series, which we're going to cover this week. What is a Fourier series? The idea is essentially to extend the analysis that we did last week beyond sinusoids to other periodic functions. So that would let us extend the idea of a frequency response to other periodic signals, shall we say. And we can do this by representing such periodic signals as infinite sums of sinusoids. That extends our work on frequency response because we can easily find the responses of an LTI system to a sinusoid, to sinusoids of various frequencies. We know that the amplitude is simply multiplied by the modulus of the frequency response, and the phase of the sinusoid undergoes a shift equal to the angle of the frequency response. So it's easy to find the response of an LTI system to a sinusoid. So if we can represent a periodic signal as an infinite sum of such sinusoids, and we simply find the responses to each of those sinusoids, and we add them up by linearity to find the response of the system to our periodic signal. In particular, we'll be able to do this for periodic signals that are what we call piecewise smooth. Sinusoids are, of course, smooth functions. They and all their derivatives are continuous. It turns out that we can approximate periodic signals that need not be continuous using this Fourier series idea. So, what's the general idea here? We're going to start out by talking about complex sinusoids. So, we should first talk about the definition of a periodic function. So we say that a function f of t is periodic with period t, capital T that is, if f of t plus capital T equals f of t for all t, for all little t. Now, of course, if f is periodic with period capital T, then it's also periodic with period 2t, 3t, 4t, and so on. So we usually choose capital T to be the smallest such capital T. So if a function is periodic with period 1, we don't say it's periodic with period 2. We say it's periodic with period 1, because that implies that it's also periodic with period 2, 3, 4, and so forth. So what are the complex sinusoids we're going to use to approximate such functions. We will write them as e to the j 2 pi n over capital T, t. And this will be for n equals 0, plus or minus 1, plus or minus 2, and so forth. Okay, so for n equals 0, this just gives us a constant. So there can be a constant component of our periodic signal. That will be captured by the case where n equals 0. If n is 1, for instance, then this sinusoid itself has period capital T. Its frequency in hertz or cycles per second will be 1 over t, and we convert that frequency in cycles per second into an angular frequency by multiplying by this 2 pi radians per cycle, and that gives us a frequency in radians per second of 2 pi over t for the case where n equals 1. So that will be a sinusoid with exactly the same frequency as our original function f of t. But then we'll include all the integer multiples of that frequency in order to be able to get a better approximation. This idea of representing signals or functions as infinite sums of sinusoids first arose in the solution of partial differential equations. If you recall our example of a PDE, it was that of, say, a guitar string, a vibrating string. And we found an infinite number of solutions for that PDE. One had the string vibrating at what we called the fundamental frequency, the lowest frequency at which it could vibrate. But we saw that there was an infinite number of other modes where the string vibrated at integer multiples of that fundamental frequency. And those integer multiples we called harmonics. So in order to describe complex motion of such a vibrating string, you would want to take account of all the possible modes and have some kind of superposition of all the possible modes. And that would take the form of a Fourier series. It would be an infinite sum of sinusoids, all occurring at integer multiples of a given fundamental frequency. So in this case, our fundamental frequency in radians per second is 2 pi over t. And we have all integer multiples of that. We'll consider all integer multiples of that and use terms involving those complex sinusoids in our Fourier series. And the reason, essentially, is that it's easy for us to analyze the effects of signals like this on linear time invariant functions. We know that these are eigenfunctions of LTI systems, and in particular, the response to a sinusoid like this is completely determined by the frequency response in the manner which we saw last week. So we can apply all of our frequency response results to find the response of an LTI system to each one of these sinusoids. So to find the response of the system to an entire Fourier series, we just apply those frequency response results component-wise to every term in the Fourier series. So this would let us extend our results on frequency response to other periodic signals. As I said, this approach works for what we call piecewise smooth functions. So we say that a function f is piecewise smooth This is essentially a sort of generalization of piecewise continuous. It's piecewise smooth on, say, the interval, the closed interval from minus t over 2 to t over 2. So that has a length of one period. of our function if there exists a finite set of points, and these are the only points where f and its derivative are allowed to be discontinuous. There exists a finite set of points minus t over 2 equals t naught, which is less than t1, less than t2, and so forth, which is less than tk, which is equal to capital T over 2, such that f and its derivative, f dot, say, are bounded and continuous on the intervals between these points. So on each open interval from ti to ti plus 1, and in addition, the left and right-sided limits of both f and f dot exist. So the limits f of ti minus, f of ti plus, f dot of ti minus, and f dot of ti plus all exist for every I. Okay, so this sort of generalizes piecewise continuity, except if you like, it requires f and f dot to satisfy the same sort of property as piecewise continuity. These are called piecewise smooth functions. And the set of all these piecewise smooth complex valued functions on the interval from minus capital T over 2 to capital T over 2 forms a vector space. We're talking about complex valued functions here in general. So the scalar multiplication of this vector space would be multiplication by complex valued scalars. We're going to introduce an inner product for this vector space, endow it with an inner product. So if we take two piecewise smooth functions f and g on this interval, and we then take the integral, take 1 over t times the integral from minus t over 2 to t over 2 of f of t times the complex conjugate of g of t, then this is an inner product on that space of functions. And we're going to use this inner product to define a Fourier series. First of all, we're going to note that under this inner product, the complex exponentials that we're going to use form an orthonormal basis of a subspace of this inner product space. So of course these are all themselves piecewise smooth functions because they're smooth functions. And in fact they form an orthonormal basis of a subspace of this space. We'll see why that is in just a moment, but this fact means that if we want to express a given piecewise smooth periodic function as a sum of these complex exponentials, we just have to take a projection of that function onto this subspace that they span. Why do these exponentials form an orthonormal basis? Well, let's take the inner product of two of them. So let's take the inner product of e to the power j times 2 pi m over big T times little t with e to the j 2 pi n over big T times little t. That's going to be 1 over capital T times the integral from minus t over 2 to t over 2 of the first function times the complex conjugate of the second, so that'll be e to the minus j 2 pi n over capital T t dt. So all we're doing is integrating over an integer number of periods e to the j 2 pi m minus n over capital T t dt. We're integrating this again over an interval equal to capital T. That capital T is an integer number of periods of this function. This function is going to be periodic with period t, and indeed with period t over m minus n if m minus n is non-zero. So if m minus n is non-zero, if m and n are different, then this is in fact going to be a sinusoid whose period is t over m minus n. So we'll be integrating it over an integer number of its periods. When you do that with a sinusoid, you get 0. So the result is 0 if m is not equal to n. And if m is equal to n, then this integrand is just equal to 1. So the integral will give us capital T. When we divide that by 1 over t, we will get 1. So this is why these exponentials form an orthonormal basis for the subspace that they span. If we take two different complex exponentials, their inner product is 0, so they're orthogonal. If we take the inner product of a complex exponential with itself, we get 1, hence it's orthonormal. Okay. So again, if we want to express a periodic function in terms of these complex sinusoids, all we have to do is take the projection of that function onto this orthonormal basis. And that defines the Fourier series. So the Fourier series is just obtained by taking a projection onto this orthonormal basis. So we just use the inner product. And what that gives us is an infinite sum, well, a weighted infinite sum of complex exponentials. And we write it as the sum from n equals minus infinity to infinity of c sub n e to the j 2 pi n over capital T times t, where again the c sub n's are obtained simply by taking the projection of the function f onto the complex exponential e to the j 2 pi n over capital T times little t, which is of course 1 over t times the integral from minus t over 2 to t over 2 f of t e to the minus j 2 pi n over capital T little t dt. So this is the definition of the Fourier series, and again you can think of it simply as a projection of a function onto the space spanned by these complex exponentials. The space for which those complex exponentials constitute an orthonormal basis. Now, often the functions that we're interested in are real valued. Here we're dealing with complex exponentials. So in the case where f is real valued, well, if you look at this integral, if f is real valued, then the effect of changing the sign of this little n here, which only appears at this point in the integrand, will be the same as changing j to minus j. So changing n to little n just gives you the complex conjugate of this whole coefficient. So if our function f is real valued, c sub n equals the complex conjugate of c sub minus n. And in fact, in that case, we can use real sinusoids instead of complex sinusoids. And we'll see how to do that in the next lecture. It's useful for theoretical reasons, if you like, to define things in terms of these complex sinusoids, because everything just works out to be a little bit simpler and shorter and more to the point. So as I said, we'll look at the formulation involving real valued sinusoids in the next lecture. To conclude this lecture, let's look at our first example of a Fourier series. Let's take a square wave. That's a pretty practical signal, one that's generated by every signal generator on the market. So let's see how we can express a square wave in terms of sinusoids so that we can apply the frequency response to it. If we're feeding this square wave into an LTI system, we'd like to be able to analyze the response of that LTI system to the square wave. We can do that using the frequency response once this has been expressed as a Fourier series, in the form of a Fourier series. So let's suppose that the amplitude, if you like, of the square wave is 1. In that case, we just have to apply our inner product to get the coefficient Cn that represents the projection of our square wave function f of t onto each of our complex exponentials. So we just have to compute these integrals in order to find the coefficients in our Fourier series. Now, I don't think I'll go through all the calculations which are given in the notes. I think I'll just write down the results. It might be tedious to go through all of that calculus and algebra. You just have to be careful to distinguish two cases when you're doing your integration. You find that C sub n equals 0 if n equals 0, and otherwise you get 1 over j pi n times 1 minus 1 to the power n. So first of all, the first part of this should make some intuitive sense or some physical sense. C of n equals 0 if n equals 0. Well, what does C sub 0 represent? If n equals 0, then this complex exponential is just equal to 1. In that case, what we're doing when we compute C sub 0 is simply to integrate f of t over one period and then divide by the length of that period. So C sub 0 is just the average value of the signal. And in electrical engineering, at least, we would call this average value its DC component, direct current component. It's the constant component of the signal. And if we look at our square wave, it's pretty clear that its average value is indeed 0. So it makes sense that we find C sub 0 equals 0. We can also see from the graph that, at least the way we've defined this particular square wave, it is an odd function. F of minus t is always equal to f of t. And that is essentially why we see that when n is even, C sub n is 0. When n is odd, this term in square brackets is equal to 2, but when n is even, it is equal to 0. That reflects the fact that our square wave is an odd function. That will become clearer when we look at the formulation of the Fourier series in terms of real valued sinusoids next time. For now, let's just write f of t is, let's say, approximately. We'll see exactly in what sense the Fourier series approximates f of t, but for now we'll just say f of t is approximately the sum from n equals minus infinity to infinity of c sub n e to the j 2 pi n over capital T times little t. That's our standard form for the Fourier series, but in this particular case it works out to be 4 over pi times the sum m equals 1, 3, 5, and so forth. So where m is odd, or rather there should be n where n is odd, of 1 over n times sine 2 pi n over capital T, t. So you can rewrite this Fourier series in terms of real valued sinusoids in this way. And in this case, we have only sines. We don't have any cosines. Sines are odd functions, while cosines are even. So the fact that we don't have any cosines represents the fact that our square wave function is an odd function. As I say, we'll talk in more detail about the representation of the Fourier series of a real-valued function f of t in terms of real sinusoids in the next lecture. For now, let's wrap this lecture up here.